Antenna parameters. Last class we have discussed some of the parameters of the antenna, like field strength pattern, that is field radiation pattern, and power radiation pattern. Okay, beam area, and next one off power beam width, first null beam width, and some problems regarding this one. And next one is radiation pattern of an antenna, and it's some technical words like major lobe, minor lobe, side lobe, back lobe, and so on. So last class we have discussed these things. Today our topic is our parameter is directivity of an antenna. Today, directivity of an antenna. All of you, please follow the last class. Please watch the video. In last class, we have discussed some of the parameters like radiation intensity, and then the beam efficiency, and the stray factor, and so on. So many parameters we have discussed in the last class, which was uploaded in the YouTube and in our college channel. So today our topic is that is, what is that one? Directivity of an antenna. Directivity of an antenna. So that is denoted by D. Directivity D, and gain is denoted by G. Today we learn what is a directivity and what is a gain, and what are the formulas regarding this one. So first of all, what is a directivity? A directivity is a dimensionless quantity. So directivity D is defined as it is uh, equal to the ratio of maximum power density, that is which was in watts per meter square, to the average value of a sphere which was observed in the far field of the antenna. So the directivity is purely regarding with a power density. So maximum power density to average power value of a sphere in the far field region. So let us look it into the formula. D equal to directivity D equal to maximum power density, which was denoted by P of theta comma phi max by, and the average power P of theta comma phi average. So this is nothing but a directivity of an antenna. Again, the formula can be represented as directivity is a dimensionless quantity, so which is the ratio of power density of a maximum value to the power density of average value on the sphere, right? So which is a greater than or equal to 1. So from this one, we want to draw some we want to write some equations which was minimized formula of a directivity, and let us look at into that one. So again, I am on a fresh paper, I am writing the formula. Directivity D equal to, what is the formula? The power density of the maximum value P of theta comma phi max by P P of theta comma phi average value. The average power density of a or a sphere is given by in our last class we have discussed the formula P of theta comma phi average equal to 1 by 4 pi integral of phi equal to 0 to 2 pi and theta equal to 0 to pi P of theta comma phi sin theta d theta d phi. This is the formula. So from this one we have to conclude that 1 by 4 pi double integral of over a surface 4 pi P of theta comma phi d omega. This d omega is nothing but sin theta d theta d phi. Sin theta d theta d phi is nothing but d omega, right? Therefore you please substitute this value in this equation. We get directivity d equal to, right, P of theta comma phi max by, okay, 1 by 4 pi double integral of P of theta comma phi d omega, right? So we can write again from this one uh, we can write the equation for our convenience like this: 1 by 4 pi double integral of 4 pi. So P of theta comma phi by this value is coming to the here P of theta comma phi max. The numerator and denominator's values are interchanged. Just I am writing the equation for our convenience only into d omega. D omega. So what this ratio indicates, P of theta comma phi by P of theta comma phi maximum, it gives a normalized power pattern. A normalized power pattern which is denoted by P suffix n of theta comma phi. So I am writing the equation like this. So 4 pi by 4 pi by double integral of 4 pi normalized P of Pn of theta comma phi d omega. So 4 pi by, which is this is the numerator and denominator. This denominator value which is indicated, which is the formula of beam area, that is omega A. So directivity from a beam area, we can calculate directivity by using two methods. The first one is this one, directivity d equal to, which is the ratio of power pattern, ratio of power max to the power average. Suppose if you know the beam area, the total beam area sigma a omega a, then automatically you can find directivity also, which is the formula of d equal to 4 pi by omega a. So this formula is in you can write here directivity 4 pi by beam area is nothing but directivity or power max to the power average is also a directivity. These are the two formulas for a directivity. Normally we can define the directivity as, it is a ratio of power density to the maximum value by power density of average value on the sphere at the far field region, right? It is a normalized power pattern. So from this equation, what we can observe is the smaller the beam area, the directivity is larger. The larger the directivity. For antenna that radiates over only half of a sphere of the beam area, that is half of the is 2, so that omega A equal to 2 pi steradian. So from that one we get a directivity D equal to 4 pi by 2 pi, which is a 2. So this is for an isotropic antenna, right? So next one, our discussion is related to gain of the antenna. Next one, gain of the antenna. Let us look at into once again. Take a new slide again. So the gain of an antenna. Gain of an antenna. Gain of antenna is an actual or a realized quantity which is less than the directivity due to ohmic losses in the antenna. Okay, so the gain of the antenna is defined as G equal to, you can write this equation G equal to K into D, where K is nothing but it's an efficiency factor. Efficiency factor, which is also a dimensionless quantity, which is 0 is less than or equal to K is less than or equal to 1. So directivity is, it is a realized quantity, that means which is less than the directivity D due to some ohmic losses in the antenna, or its or if it is closed. In transmitting, these losses involve power fed to the antenna, which is not radiated but heats the antenna structure. So by using this formula, we can find the gain of the antenna. Here K is nothing but efficiency factor. So in many well-designed antennas, K may be close to the unity. K may be close to the unity. In general, G is always less than D. Make it a point. In practice, G is always less than D. With D, its maximum mileage value. So gain, another formula. Gain can be defined as gain equal to G equal to power maximum by P max with a reference antenna. Okay. So this is power maximum is under test, under antenna under test, into G, reference antenna. Reference antenna. Again, we can write, we can explain, we can elaborate this formula once again. Gain equal to, suppose if you take one antenna as a test antenna, that is a ideal antenna. So P max AUT is nothing but antenna under test. Antenna under test. So P max by P max with reference antenna into G and gain of a reference antenna. You know the gain formula, G equal to K into D. So K is nothing but efficiency factor. So this is one of the formula for uh, gain of antenna. If the off power beam is, if we know another formula for gain of the antenna, or a directivity of antenna, we can find the directivity of, if you know the directivity, we can find the gain. If you know the efficiency factor, we can find out the gain. So this is the vice versa. So if we know the directivity D, having another formula, if that is 41253 square degrees. What is this square degrees? We discussed in the last class. If you have any doubts, please refer to the last video. So 41,253 by theta of power beam width into phi of power beam width. So for 41,253 is nothing but number of square degrees, square degrees in a sphere, in a sphere. Theta HP means of power beam width in one principal plane. Phi HP means of power beam width in other principal plane. So directivity D equal to approximately, we can for our calculation, directivity D is equal to 40,000 square degrees by theta HP of power beam width into phi of power beam width. This is an approximate directivity. Approximate directivity. So this is about, what is this one, gain of the antenna, and the last one is uh, directivity of antenna. So coming to the conclusion, directivity D is a purely the ratio between power density maximum value by power density average value, and another formula is 4 pi by total beam area, and the directivity G is some, what we call, it is a realized quantity which is less than the directivity. We can write the formula G equal to K into D, that is the directivity. Here K is nothing but efficiency factor. So K is less than 0 is less than or equal to K is less than or equal to 1. Another way of defining a gain is when we have antenna under test and a reference antenna and the gain of a reference antenna. If you know the square degrees of the antenna, radians in steradians, so there is a directivity for a formula, directivity D equal to this one, 40,000 of square degrees by theta HP into phi HP. Okay, in our next class we can do some problems regarding a gain and directivity. So all of you please, once I write what are the antenna parameters up to now we have discussed. First one, radiation pattern. Radiation pattern. What is this one? Radiation pattern. Radiation patterns are two types: field radiation pattern and power radiation pattern. Next one, a 3D radiation pattern. What we observe: a major lobe, minor lobe, okay, and some other thing, side lobe, back lobe, and what is a null, these things. So from this one we have observed next section of power beam width and first null beam width. Here we find a field strength units, which is E of theta comma phi, which is nothing but volt per meter, and field strength and power strength. So on the next one, what we observed is a beam area, total beam area of a sphere. So beam area is nothing but we have some average uh, power, average normalized power over a sphere, which was given a formula beam area. So under d omega, what is d omega? So sin theta d theta d phi, which is d omega. And from this one and next one we have observed after beam area and antenna efficiency, sorry, what is next one? Radiation intensity. Radiation intensity, which is denoted by Pn of theta comma phi, which is denoted by u of theta comma phi by u of theta comma phi maximum. There is another formula is also there for radiation intensity, in terms of pointing vectors, s of theta comma phi by s of theta comma phi maximum, right? And beam efficiency, next one is a efficiency efficiency, which is denoted by epsilon m. So this is a sigma m by sigma a, that is main beam area by total beam area, which gives a beam efficiency. And next one is stray factor, which is a small, this one is a capital M. If it is a small m, this is what we call a stray factor. This is a minor beam area by total beam area, which gives a stray factor. And next one, last right now, today's class, directivity and gain. These are some of the parameters of the antenna. You please study these parameters, and next class we will look at into another parameters. Thank you.